there. Pick a pair of safety glasses.
Take a break.
Well, it does smell of burnt pickle down here, I must admit. Are you coming down? All right. What's your name? What's your name, sir? Your name? Christopher, okay. There are some safety glasses for you as well. So each you grab them. I'll let you dress yourselves. All right, Alex, dipper or pointer? Dip, all right, so you're a pointer. So what you're going to do is you're going to dip this rod into liquid nitrogen. That's your job. You need to wear safety glasses, please. And you'll wear these gloves as well, because you're doing a cryo. All right, so you step over there, please.
Your name again?
That was what Spider-Man used the first time he was fighting like
Krista, your job is to do some pointing. Now, this is a flashlight here. It's not particularly bright. And you need you to stand over here. And we are going to point this at these solar panels up here. Now, they're connected to some LED strips. When they get light, the light from here should generate enough electricity so we can get the strips to light up. But we're going to see whether this is bright enough. Now first, I'm going to put that down here and instruct Alex what he's going to do. Now, this is our setup over here. I have a light, which is a car headlight. I have it going through the electricity going through the black cable. It goes through a transformer inside. We're going to use that word transformer again. To the white cable, and that goes to this large coil of copper wire. Now, it loses a lot of energy going through this long journey to get to the light bulb there. So it loses the energy is in the form of heat. So just take one of your gloves off for a moment and just feel that and tell me if it feels like anything. It's hot. So does it feel hot? So we're creating heat energy there. And I want the heat from there to go. Hey, you're not allowed to laugh at people on the stage, otherwise you come down on the stage. I mean, that's fair. You know, they're here because they volunteered to do so. They deserve people you respect, please. Now, so the energy, I'm losing a lot of energy in form of heat there, and I want that heat to be in that bulb over there, because if it gets that bulb lighter, it gets brighter, and then we can point at those things there. So you're going to hold this, and I'm going to open the liquid nitrogen. Now, the temperature of liquid nitrogen is minus 195.8 degrees Celsius, so it's going to rapidly cool itself down. So we should lose that heat there, because the electrons don't want to hang around in there. It's too cold to hang around in there, so they're going to rush out of there as quick as possible, and then go over to there. So your job first is to hold this up, it's a bit heavy, 2 hands, and point it at those panels there and see does any light come on. Now, let's have the lights down. We don't want any other lights coming from anywhere in the room. So, is any lights on that whole screen, is any lights on there coming on at all? No. Right, I'm going to ask you to place this into liquid nitrogen. And we'll have the screen of down here, have the camera down here so we'll see what's happening down here, please.
Oh, it's getting actually bright.
All right, so I'm looking at there. All right, now, sort of moving it around from one to the other. Let's see if something. Does it look like it's getting brighter at all? Because if it,
oh,
right, try another one. Try another panel. That one works. Try the one lower one. Oh, there you go. Lights on top. Try the panel up over there.
That's right.
Well, hang on. If it gets brighter, see, red is a nice low energy. Now, if we get any other colours other than red, it means we're getting brighter. So we'll try up there again. Let's see if it makes anything go. Oh, yeah. Was there something over there? Yeah, go past the middle one. There you go. So, if you move it, wave it around a bit, we'll see that other LED strip come on. Let's see it go across there. Oh, there you go. It's blue. And what about down the bottom now? If you got that one there, that's a red. All right. So we're making the heat from there go there. We're allowing the electrons to move through. We're reducing the resistance. There's so little resistance when it's so cold. This is getting brighter, making the LEDs go on because we're generating electricity with a solar panel. Okay, let's give my volunteers a round of applause, please. They're very welcome. Take them out, please. And ask you just to place it on top of there. Thank you so much for doing that. So, by cooling it down, we allowed the electrons to really run through there at breakneck speed, and they gave up their energy in the filament of the light, and the light energy we transferred over there, created electrical energy, which also gave us light energy again. Okay, let's move on to the next slide over here. I get control of that. So that's our resistance there. R stands for resistance, and the lovely thing is the squiggly lines, and it just shows, and this is the best part about illustrating electronics, is that it takes so long, that much energy to go from, oh, that's not working, let's try this one. So much energy to go from there to there, but there's a lot more roads to go along here, you use a lot more energy, so that's why we have those symbols for resistance. That's a symbol for energy coming in, negative, positive. Always think that one is positive, because you can take that, put it on there, it makes a positive sign. All right, so heat, light, that's where our resistance was. Let's talk about alternating current. What exactly is alternating current? We use the word DC. Let's bring your attention back to the galvanometer over here. I have a magnet here, it's called a cow magnet, and it will fit inside this coil. Now, I'd like you to look very closely at this when we get the camera up here. And we're going to look closely, we're going to try and zoom in here, if possible. Right, that's good. I can go on the other side, so I can see better. Now, if I place this in here, I want you to notice what the pointer does. It goes from one side to the other, one side to the other, one side to the other. It's alternating between one side and the other. It's an alternating current, or AC. And moving a magnet within a copper coil makes an AC current. And this was the coolest thing. This is Michael Faraday came up with this idea. And it was kind of an accident because of a guy called Hans Christian Ørsted, who had to have a compass by his battery. So let's go get a volunteer out to do a little alternating current experiment over here. I'm going to go to this person over here, if you don't mind coming out. This one I don't even need to wear a lab coat for. Now I have a coil of copper wire here. There, a coil of copper wire. And I'm going to connect it, what's your name? Lucas. I'm going to connect it, I'm going to ask you, whilst I go over there, to connect these clips to two terminals there, and I'll copy you right back. I need to get a magnet. I'm just going to... Okay, so, I'm going to give you one of these. These are magnets here. So Lucas, hold this magnet in your hand there. Now, just step back over there so we can see this. Yeah, that's a good place. Just move that over there so it gives you a little bit more room. Right, now, I'd like you to take the magnet there and just make circles around that copper coil. Now, can you see the needle moving? Mm-hmm. You see it moving two directions. Yes. Lucas is a human dynamo. He's making electricity, and all he has to do is move a magnet around a copper coil. Now, if I asked him to do this like 365 days a year, 24 hours a day, he'd get pretty tired, and I'd most probably have to feed him. So I've got to find something else to spin that magnet if I want to make large amounts of AC electricity. And AC is what we get up the walls, so we need that AC electricity. So I've got to replace Lucas with something that's a little bit more efficient and somebody I don't have to feed. But anyway, let's give Lucas a round of applause for being a marvelous human being over here. Okay, now let's place that down there. Now, we've got to go back in history here to find something that spins. Let me just put that away. And let's go back to our PowerPoint. Okay, so, very important people here. Hans Christian Ørsted, 1820. There's a compass sitting on his table there. He's got a battery, that's Volta's pile. That's 21 years new. That's what was invented for 21 years later. And he's connecting the wire up. Now, when he connected the wire up, something weird happened. The compass needle started to swing. Now, we know that the only thing that makes a compass needle swing is the planet or a magnetic field. And Ørsted didn't have a magnet anywhere near him, and so he didn't know why it happened. But he realised that every time he connected a battery, the compass needle swung, and he wrote about it. This man here, Michael Faraday, said, hey, that's very cool. And he figured out that if you moved a magnet around a copper coil, you made electricity. And that's cool, because that's how we make all our electricity. So at the time, he's your Einstein of the day, he's your Isaac Newton. Very humble beginnings, but a very, very ingenious person. Now, we use the same techniques today, so let's see how we can generate some kinetic energy or some movement using perhaps another energy source. And we could use water and wind. Those are totally renewable, but we do tend to burn a lot of things. So I have a device here which was first kind of demonstrated over 2,500 years ago. It's called Hero's engine. The guy was Hero of Alexandria. You can look him up. His name was Hero, and he lived in Alexandria. Now, my heat source is coming from gas here. So I have gas in there, which could be coal gas, it could be butane, propane. That's my chemical energy. I've converted it into heat energy and light energy. I'm going to heat the water up in this vessel over here. Now, as you know, water is going to get to its boiling point, and which is 100 degrees Celsius. I think you can see me there. And you'll see the water start to heat up and start to boil. It'll change its state, go from a water into water vapor. The water vapor is going to come out of these two nozzles at great speed. We'll see it come out as steam. Steam is actually liquid water in a tiny little droplet suspended in the air. Water vapor is obviously, as you know, a clear and colourless gas. Alright, so I can see there's some convection currents happening here, some condensation happening, so I'll just let it heat up. Whilst I'm waiting, what's the boiling point of water at sea level? Anyone? Call it out. 100 degrees Celsius or Fahrenheit?
Celsius.
What was that? Celsius? Yes, Celsius. All right, so, and that's the beautiful thing about the Celsius. And actually the metric system, like 1 litre of water is 1 kilogram, 100 degrees Celsius is a boiling point of water, 0 degrees is a freezing point. Very, very convenient. All right, so now we're getting some bubbling. We're waiting for some vigorous bubbling, so I really want to generate some pressure build up. Now, the two nozzles there, I've crimped them down so that when the water vapor comes out, it comes out with as much velocity as it can. All right, we're getting there now. We shall see some steam. There's water vapor now, but you cannot see water vapor until that happens. And then once that happens,
Whoa.
It builds moment.
and there's your kinetic energy. Now, if I put magnets on the outside of that, I've now got spinning magnets. And I put a coil of copper wire around those spinning magnets, I'm generating electricity. And you can use heat to do this spinning, you can use water to do the spinning, you can use the wind to do the spinning, you can use the tides to do the spinning. You need to get the kinetic energy from somewhere to move the magnets and the copper coils together. And once you're doing that, you're generating an abundance of electricity. Yes, I like the way the vortex inside as well. It's very cool, the vortex. All right, so let's move on a bit. Let's get back to our screen here. So movement gives electricity. Movement could be steam power. So that's the first one, the steam engines, and the nuclear engine. Coal, heat, water, water vapor, atmospheric pressure, reciprocating engine. So, heat, movement, electricity, do a lot of that. But let's talk about transformers. That's Bumblebee, I think. Is that Bumblebee?
Yeah.
Who's that? So that's not Optimus Prime, surely. I thought he was
It's
red,
John.
red and blue, Optimus Prime. Anyway, we're not talking about those kind of transformers, but the reason I put it up there is because, well, pop culture is very, very useful sometimes to illustrate things. We talk about transformers when it comes to, and you might have seen these kind of transformers by the side of highways, perhaps in parks. These transformers take a very high voltage and they step it down a bit. Now, I'm going to move things around here a little bit here. So, we're talking about high voltages here, and today we're going to do a high voltage electricity with this device over here, the Tesla coil. We're going to be dealing with about 250,000 volts of electricity. Now, transformers. You plug in your laptop, you'd most probably, you can get to the front here, and we'll get the camera down here. Get the camera down here. I'll wait for it. Laptop transformers. Camera, please. There I am. Right, so you might have seen these, wall wart, they are transformers. It's called an adapter, and you'll see on it things like, it will say what the input is. In this case here, it's 120 volts AC, that's what's coming out of the wall. And it says 60 hertz, and that's 60 cycles, so that's up, down, up, down, up, down, of a curve for 60 times a second. AC output is 12 volts on this one here. Sometimes it says DC output, but this is AC. If we open it up, that's the little device inside. So you've got your primary that goes in, so that's coming from the wall. That's coming from the wall here. So that's primary. Secondary is what comes out. So 120 in, this comes here, 12 volts out. It transforms it. Now, sometimes it transforms from AC to DC, and you need something called a rectifier. This is a larger version here, so these are what is going in, this is what's coming out. Anyway, we're going to use transformers today, a very, very large amount of transformers. Let's get our PowerPoint back, please. So there you go, step up, step down. And step up means like you can, say, run a pump for an air mattress, which runs on 120 volts from the cigarette lighter of a car. Not that they have cigarettes anymore. But that means it's 12 volts in, 120 out. So that's an inverter. A transformer goes from a large voltage down to a smaller voltage. Now I'm moving things to the side of the stage here to clear the stage for a presentation of the Tesla coil, named after Nikola Tesla. One of the things he used to play around with. And he's holding in his hand a fluorescent tube. I have one over here, the fluorescent tube here. And I'm going to ask you to hold this during the presentation, just by holding it like that. Like that. It's glass, so be careful with it. At some point, when we fire this, look at that. All right. So, Tesla coil is a series of transformers. See here, it's how it works. We're going to build up a voltage, and we're going to release it very quickly. I'm going to be inside this cage here, which is called a Faraday cage. Inside a metal box, like inside a car, is a very safe area to be in a high voltage situation, like a lightning storm. Now, we are dealing with very, very high voltages here. So, words of caution. Pacemakers. We've got a pacemaker here. So we'll ask you to maybe leave the auditorium to have a pacemaker. 250,000 volts. All right, so let's ask this question before we go any further. We need to re-poll this, please. Okay, just make sure I get all the instructions right. And this will have a sound to it. You may want to video the reaction. I will be in the cage and I'll be wearing these ear protections here. It's not unbearably loud, but if you do not like loud noises and you wish to protect your ears, please place your hands in front of your ears like that. We're not firing it just yet. All right. So, do we have 64 people? Let's see. Why is the Faraday cage safe? This is a question mark at the end of safe.
Oh, we have this question.
You'd also be safe inside a suit of armour as well. Okay, well, let's see what 78 people have to say, and we can go and fire this thing. Ooh, look at that. Right across the board. Electricity always takes a path of least resistance. Yes, it does. The metal cage is a path of least resistance on the outside. Yes, it is. The metal cage directs the electricity flow to the ground. It does. The metal cage prevents external electricity fields from entering the inside of the cage. All of that is very true. Excellent. All right, so safety protocols. When I fire this, nobody gets up and walks around at all. The doors nobody will be entering from the sides here. We have a safety laser system over here. If anyone steps down here, the Tesla coil will not fire. So we have a safety area with a series of lasers that fire across the front over here. It's very, very high voltage. Do not get up during the program, please. Now, Nikola Tesla, there he is. Very, very interesting man. And let's see, if I've got anything else before I go in and fire this up. No, that's the end, so that's the bad one. All right, so I'm going to fire up the Tesla coil. I can do 2 or 3 sparks out of it. If you're ready for this, protect your ears as necessary. We'll turn on
I don't need it.
That's it. Okay. Oh, I see why. Richard? Right, resetting. What's the close? Oh, over there? Over here?